So from the homework yesterday, here's 10C. One fraction equals one fraction. Yes, one complicated ugly fraction equals one complicated ugly fraction. But stuff can move diagonally. So the first thing that I did, I moved the t squared to the top. I imagined the t squared there. And there's the equal sign in my mind. Then I took that big G, that big M, and that little m, these three, and I said they'll move to the bottom. You okay with that? I left the lowercase m and the 4 and the pi squared where they were because I don't want to move them to the t side. I'm happy with them where they are. There's already an r there. And then I took this r squared and I also moved it up to here. And what that meant is I had an r and an r squared, and I said, wait a minute, I think that's r cubed. R times r times r. Deegan, that gives me a t squared. How to get rid of a squared? Okay? Now, in part D, you're going to get the r by itself. You're actually going to end up with an r cubed by itself. How do you get rid of a cubed? You cube root it, which you've seen, I think. You may have wondered, we're actually going to use cube root on your calculator later on this year. Yes, it will actually come in handy. Is that all right? Okay. Any others from the homework? Yeah?
The 8 of vector and x.
Number 8?
Yeah.
Okay. Key idea here is it's the angle of depression. So if I draw a picture, this is 120 meters high. This angle here is 37 degrees. That's the angle of depression. And they want the, oh, there's a boat here. There's the boat. They want this distance. Okay. So I have two options. I can't use this 37 where it is. It's not in my triangle. I can either say that this angle right here is 90 minus 37, 53. Or I can say that this angle here, color, is 37 degrees, color. Doesn't matter which one you do, you'll get the same answer no matter what. I usually do that, move the 37 down, and then I could go opposite, adjacent. I think it's going to be tan 37 equals 120 over x. X is going to be 120 over tan 37. Whatever the heck that is, I don't know. So this assignment is technically due today, and what I mean by that is you're going to get more homework today. Not very much, actually, but it's really going to start to pile up Monday. That's when we really start to hit the road. But today is probably the single most important lesson of the unit. So if you have it done today, if you finish this, you can hand it in back there in block C. If you need to finish it over the weekend, that's fine. Not a problem. Recall from last year. You ready? Good, shut up. Recall from last year. In physics, all measured quantities are either scalars or vectors. And that is going to become much more important this year. Scalars have magnitude only.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Oh yeah!
Scalars have magnitude only. Vectors have both magnitude and usually someone also says, oh yeah, okay. Vectors have magnitude and direction. Scalars have no direction, much like your futures. Okay. Patrick the puppy goes wandering around his neighborhood as seen below. So it looks like he walks 3 meters and stops, 2 meters and stops, 4 meters, 4 meters, 2 meters, 4 meters, and finally ends up right there. Notice a series of arrows drawn on the map of a physics teacher's front lawn. Each arrow shows the magnitude, size, and direction of a series of successive trips that Patrick the puppy made. These arrows showing magnitude and direction of his displacements are called vectors. When Patrick reaches his final spot near the car door, how far has he walked since leaving the porch? It depends on what you mean by how far. If we're talking about the distance, it seems to me that it's 3 plus 2 plus 4 plus 4 plus 2 plus 4. I just read the numbers on the arrows. Which is what? Yeah.
It seems that the last angle is an angle.
Don't worry about that yet. I'm just saying, which is what? I think 19. Yes? The displacement, which is the change in position, is just that. And if I redraw that, I think I can tell you how long this vertical side is by looking at the original diagram. And I can tell you how long this side is. And so if this is the displacement, I think I can figure out how big that is using something that starts with the letter P and rhymes with Pythagoras. Good, get your calculators out and hopefully without writing anything down to 1 decimal place, tell me what the displacement is. Is it 5? Even? Great. No, that's wrong. That has to be wrong. Because a displacement has to have both magnitude and direction. Okay, the magnitude is 5. How am I going to show the direction? There's 2 ways to show the direction. One way is you can put it in square brackets. Don't forget the square root. Yeah, right? 3 squared plus 4 squared equals square root. You okay, Deacon? Yep. I tend to show direction by putting an @ symbol, like what goes in front of a Twitter handle or second function, the number 2 on a keyboard. And this is what we would say: 53 degrees east of north. We'll talk about that east of north dealio in a second. Malcolm, could you shut that door for me? Thank you. Some people came in late and didn't close the door behind them. Now, there's 2 ways to show that something is a vector. In a textbook, they'll do vectors in bold font. So that would be, say, velocity. But doing bold font when your handwriting is dumb. So we show vectors by putting an arrow over the top, but we get lazy and actually end up only putting half of the arrow part over the years. So to show a vector, I put an arrow above it. That's indicating it's got direction. If all you care about is the magnitude of that vector, you don't care about the direction, you just want to know how big it is. In a textbook, they'll use italics. Again, italics is really, really tough for us to write. So in handwriting, we'll use the absolute value symbol. You learned the absolute value symbol in math, and Rachel, you thought, oh, I just make a negative number a positive. No, actually what it was saying is, who cares about the direction on the number line? What's the magnitude of how far you traveled on the number line? It is actually behaving in math the same way it does in physics. If you add 3 kilograms of sugar to 2 kilograms of sugar, you're going to get 5 kilograms of sugar. If you add 3 liters of water to 2 liters of water, you're going to get 5 liters of water. That's because mass and volumes are scalars, and they follow the rules of scalar arithmetic. They have magnitude, but they have no direction. What are some other scalar qualities? Do you remember any from last year? Speed, which we showed with a V with no vector sign above it. Time is one big one. There are many other. Area, for example, don't write that down, but area is a scalar. Oh, that has an area of 4 square meters north. Makes no sense. Okay. One big one that we normally would have got to last year, but that we didn't because of COVID, energy is a scalar. When we look at work and energy this year, we'll analyze roller coasters, because if we didn't use energy, we'd have to take into account every bump and every raise and every drop on the hills. We need to know how long they were and what angle they were. Ugh. It's doable, but it's ugly. Or use a scalar approach that doesn't care about direction at all. If you add a 3-meter displacement to a 2-meter displacement, well, it can add to 5. 3 right plus 2 right is 5 right. It can add to 1. 3 right plus 2 left is 1 right. Or it can add to any decimal in between 1 and 5. 3 right plus 2 up, or 3 east plus 2 north. You actually end up with a magnitude of 3.6. By the way, this picture here, these vectors were combined using the rules for vector addition, which we'll talk about in just a few minutes. So in addition to displacements, who remembers some other vector quantities from last year? Yep. Although often we just found the magnitudes, especially in forces, because we had things accelerating in different directions if there was more than one mass. So we just said, find the magnitude and look at the picture and figure out the direction yourself. Force, by the way, matters which way you push on something. Now, the way we did it last year is, instead of teaching you vector math, I used winner minus loser. But really what I was saying is one direction will be positive and one direction will be, okay? That works great for one-dimensional vector mathematics. Another vector, momentum, which we didn't get to last year. Sorry? Displacement would be. So suppose I have 2 force vectors, 7 newtons and 4 newtons. What's the maximum force I can get by combining them? What's the minimum?
3.
And I can get every value in between. That 53 degrees east of north, let's look at that. Turn the page, please. To show the direction of a vector, we focus on the angle where it originates. So we're going to be doing a bunch of compass directions. As soon as I'm dealing with compass directions, somewhere on the page, I always write a little compass rose, because the number of times I've botched that would amaze you. So anytime I see the word north or south or east or west in a question, first thing I do right away, Logan, I write down one of those. In fact, I probably won't help you if you have a question from the homework and I see a direction and you haven't written a compass rose, I'm walking away. What direction is this vector here? Well, I don't know whether this is a force vector or a displacement or an acceleration. I don't care. I just want to focus on the directions. So I'm going to go at, this would be 28 degrees north of east. Now, how the heck did I get that? You'll notice this vector is made up of two lines, a slanty line and a nice line. The nice line always goes after the of. And then you ask, if I go to that nice line, what direction do I need to go to get to the slanty line? Go east, go north of east. Let's try the next one. How would I write this one? This is 51 degrees north of south, east of west. What of what?
51 degrees east of north.
This is east of north. Start out going north, go east of north. This is 20 degrees north of south, east of west. What of what? West of north. If you find this tricky, don't feel bad. One of the strongest students I ever taught, a kid named Dylan Gattner, about 12 years ago, also one of the best basketball point guards in the province. He was on the all-star team. He could not get this. He tried and he could not understand this. So he wrote out all 16 possibilities and memorized them. So he just wrote every possibility way you could write it. Try and understand it. But if you have to memorize your way to it, it can be done, but I wouldn't. Yep, somebody at the door. Give me 1 second. Hang on, let me just hit pause on the video. Record. Hey, what'd you say? 48 degrees, what of what? North of south, east of west, what of what?
Southwest.
South of west, I agree. And of course, you were all clever enough to try this one on your own. And what about this one?
Southwest.
Actually, for each one of these, there are two possible answers. And so what you're going to notice in the answer keys that I give you for the first few days, I will put both answers. Eventually, I'll stop because I'll assume that you've clued in. There's two answers, and if my answer doesn't match Mr. Dewick, it's because I found the other one. Let me show you what I mean. Let's go back to the first one. It's possible that when you set up your vector diagram and your triangle, you ended up finding that angle. How big is that angle? It could also be 62 degrees east of north. I would accept that as well because you'll end up at exactly the same spot. It may just be that you drew your diagram differently from me. That's all. What if you had found that angle? That would be at 39 degrees. What of what? North of east. Fancy word, this is the complement of this one. Right? You just clicked, figured it out. Yeah, they add to 90. And you can either use your calculator or do the math in your head. On a test, I always use my calculator because the number of times I've forgotten to carry the one when I've done it in my head. In my homework, I try and do everything in my head, but on a test, I would type it in just so I don't make a dumb mistake, right? Ooh, what would this one here be? 70 degrees north of west. Start out going west, go north of west. What would this one be? 42 degrees west of south. Are you actually calculating the west of south, or have you noticed the pattern, right? These actually just swap as well. So the last two, this can also be at 12 degrees south of west. And this one can be at, so here's the common mistake that I do if I'm doing this in my head. I'll go, oh, that's 48 degrees west of, and it's not 48 degrees, what is it?
38.
Yeah, that's the easy mistake to do if you're doing it in your head. So just be careful and make sure you carry the one. I will take either, and in the answer keys for a while, I'll put both, but probably after about lesson 4 or 5, I'll just stop and assume you'll figure out, oh, he got 52 degrees south of east, I got 38 degrees west of, why did I say west of east? How about west, wow, did I botch that? South of, let's try that again, Mr. Dewick. East of south. Yeah. I'll assume that you'll clue in. Yeah.
So it'll always be if your answer is the right answer, to add with your answer to 90 is correct?
And the what of what's are opposites of each other. Okay. Typically, I will do my diagrams in the order that they gave me the stuff in the questions. So if you do that, our diagrams will look the same. But every once in a while, it will become obvious that it's way, way easier to change the order because it makes the question easier.
Yeah.
And so your answer might look different. Here's the entire point of today's lesson, so focus up. First of all, vector addition in one dimension. I snuck that in a little bit last year. 5 meters each. Oh, I see a compass direction. I'm going to put a compass rose because I will. What's 5 meters east plus 3 meters east? What's 6.2 newtons left added to 6.7 newtons right? Unless you're Alessio. Alessio said negative 0.5 newtons left. And that explains a whole bunch right there about Alessio, doesn't it? Why would you double don't. The third vector, that answer, represents this. Yep.
For the example 2,
Mhm.
do you have to put the half
Nope.
there? Okay.
And in fact, I often don't put it there. Now, here's the problem, though. In this first one, there's going to be one later on when there's going to be an N. Is that newtons or north? It all depends on if it's after the at symbol or in front of the at symbol. Is that west or watts? All depends on if it's after the at symbol or in front of the at symbol.
Okay. So it's good to have on there, but not.
Yep. The third vector represents the sum. We have a fancy word. When you add two vectors together, the answer is called the resultant. And I'll use that word because it's nerdy. I snuck this in last year. When I was doing winner minus loser, I was sneaking in one-dimensional vector mathematics. We just didn't call it that. Here's the new stuff, adding vectors in 2 dimensions. We represent vectors with arrows. One way you could add vectors in 2 dimensions would be to very, very carefully draw them to scale using graph paper, a ruler, a protractor, and then carefully measure the distance between them. Ugh. So, John travels 5 kilometers west, then 8 kilometers north. What's his resulting displacement? You could do that with graph paper, but there's a better way. We could use trig. So here is the rule, and it's in bold font. This is what you're going to need to commit to memory. If I want to add 2 vectors together, I draw them tip to tail. How do I add 2 vectors together? Draw them tip to tail. How do I add 2 vectors together, Kessler? Draw them. Rachel, suppose I want to add 2 vectors together. Any suggestion on how I want to draw them? That's pretty good. Parker, I want to add 2 vectors together. How should I add 2 vectors together? Draw them. Okay. Everybody, if I want to add two vectors together, how do I draw them? Now, what does tip to tail mean? Okay? Put your pencils down, look up. You're like, what have I gotten into? Welcome to my class. Okay? Here's a vector. Here's another vector, and I'll just change its angle. Suppose I want to add those two together. I will draw them so that the tail of the second vector is on the tip of the first vector. And then, if we go back to our notes, the resultant is the line from the tail of the first to the tip of the second. The resultant is that line right there, from the tail of the first to the tip of the second. How do we add two vectors together? We draw them tip to tail, and then the answer, the resultant, from the tail of the first, pointing towards the tip of the second. This is not a right angle triangle, so you can't use Pythagoras. You would have to use the cosine law and the sine law. But this year, 99% of what we're going to do is right angled. You got a question?
Does this also work if there are three vectors?
Patience, grasshopper. Great question. What if you're adding three vectors? Hold that thought. We got one coming up. Okay, so let's do example 4 here. You don't need to look at your phone. It's not that important. Let's do example 4 on the next page. And then, does anybody remember, what does DALP stand for?
Draw a little picture.
We're going to draw a little picture. So they've all had me before. DALP is draw a little picture. Here's what I mean. First of all, the fact that I see the word west, Parker, leave them alone, west and north, I'm going to draw compass rose. Okay? The first vector says 5 kilometers west. So I'm going to draw something pointing west, and I'll label it with a 5. I'm going to try and draw these roughly to scale, and what I mean by roughly to scale, the next vector is 8 kilometers north. Is 8 bigger or smaller than 5? Twice as big? So if I eyeball an 8, how about like that? Give or take, roughly to scale. I want to add those together. How will I draw them? So what's it going to look like? Everybody look up and watch. Here's the first vector. Here's the second vector. And the resultant, the displacement, is from the tail of the first to the tip of the second. Draw that. This is an equation. This is a vector equation, and it's a bit weird because you're going, we're adding shapes. Yes, we are. Absolutely. This is 90 degrees. How can I figure out the magnitude, how big D is? I'm looking for a word that starts with the letter P and rhymes with Pythagoras. On your calculator, go. If you can do it without writing anything down, if you can go straight to Pythagoras and tell me the answer, great. 9.43? Units? And of course we're wrong because this is a vector. We need a direction. Where do we get the direction from? Look up. Theta always goes where the vector is coming from. Not where it's pointing to, where it's coming from.
North of south.
Color, 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 color. This 8, opposite, adjacent, or hypotenuse. That 5, which trig function? Tan theta equals what over what? 8 over 5? How do I find theta? This is not stuff moves diagonally. How do I find theta?
Did it by itself?
No, I can't. It's inside the tan. Shift tan, or shift cos, or shift inverse. So how big is theta? Inverse tan on your calculator, please. Which one? 58, if we round off properly? 58 degrees north of south, east of west. What of what?
North of west.
Well, it's either north of west or west of north, because those seem to be the two. Which one? Remember, This is going to go with the of. So of west. What of west? Or same magnitude, 32 degrees west of north. Mr. Dewick, how would you get that? What's 5 plus 2 in your head? What's 2 plus 5 in your head? When you add, does the order matter?
No.
So I added 5 plus 8. You might have drawn 8 plus 5. You get the same resultant as before, but you're going to find that angle, which is west of north, and I can even tell you how big it is.
Why did you find the hypotenuse?
You had to find the hypotenuse. You couldn't do it without.
Oh.
Okay? So, how do we add two vectors together? Everybody draw them tip to tail, and then from the tail of the first to the tip of the second. Suppose I have two forces. F1 is 10 newtons due east. F2 is 6 newtons due south. Find the resultant F, and then I use a subscripted R for resultant, because that seemed to make sense to me. Dolp. I've scrolled down. You might have a compass rose on your page, but I don't, and I see directions. So the first thing I'm doing is putting a compass rose. Also because now I feel better. Nick, what's the first vector? Can you read it to me, please? Magnitude and direction. What does N stand for? No. Newtons. Is there an at in front of it? Not. And this is why, remember last year I told you a bunch of times, we don't have enough letters in the English alphabet? I wasn't kidding. So I got to keep everything in context. 10 newtons, direction, stop. So 10 plus 6, bigger than 10, smaller than 10? Half as big? A little bigger than half as big, eyeball it. I'd like to add those two together, Nick. Any suggestions on how I might want to draw them? Tip to tail, you say. You could draw the 6 first and then the 10. I will almost always draw my solution keys in the same order as they gave me the numbers. So since they gave me the 10 first, I'll do that first. So if you want your answer to look exactly like mine, that'll happen. So Nick, you're saying that, and that the resultant should be that there? Where's theta going to go? Top left or bottom right? Where the vector is coming from. Color, color, color. Solve this on your own. I'm going to do this without saying anything quietly. If you get stuck, look up. I got that. Am I right, first of all, or did I make a mistake? Okay. Spencer, question.
Will you take 11.26?
We go to 3 sig figs. in our final answer. So I would take it, but I would also say, really? Is your calculator working okay? Yeah? Okay. We went through all this yesterday with the calculator stuff, so I'm kind of throwing you in. Alrighty. You all right with that? Yeah? I like example 6. I like example 6. I like example 6. Example 6 is a nice question. My students from last year, can you explain to my new students, why did I say that?
Because it's on the test.
Did you hear me say it's going to be on the test, or you just pay attention when your teacher emphasizes certain things? Okay, good. You figured it out? Okay. This is a nice application. A plane is flying due north. Stop. Nice try, Mr. Duke. Plane is flying due north at 132 meters per second. A crosswind is blowing due east at 44 meters per second. What is the plane's resultant velocity relative to the ground? It says, hint, write an equation, then dope. Look at your blue formula sheet, please. I used to make kids derive this, but I've mellowed out. I think I gave you the airplane crosswind equation. Shay, did I not? Shay, can you read me that equation, please? Sorry, you're going to try it again a little quieter. Go ahead. There's something in front of, there's a letter above the word engine. I'm sure there is. No? What does the V stand for, people? Okay, go ahead. So I'm going to abbreviate with an E. Yep, keep going. I'm going to abbreviate with a W. This is we're arguing the plane pushes itself. The wind also pushes on the plane. The combination is what the ground radar sees. You okay with that? You all saw where it is, by the way, I hope? Yes? Okay. Which one are we trying to find, Shay? So I guess they gave me the other ones. What is the plane's engine velocity? Can you read it to me, magnitude and direction? Now, you're going to be a little uncertain. Which one is the wind velocity? So the other one's got to be the engine velocity. What's the plane's engine velocity, magnitude and direction? Direction? Okay, so, yoink, 132. Wind velocity, magnitude, and direction. 44, bigger or smaller than 100? You know what? It's about 1/3, isn't it, roughly? So I'll eyeball it, yoink, about like that. And I do that so that my diagram answer looks okay. Shay, I want to add those together. Any suggestions on how I might want to do that? No, really? Okay. So it's good. Oh, every year I have some kid who wants to get these wrong. Because here's what they do. Draw your triangles big. Bigger is much better here. I gave you plenty of room. I gave you at least a half page, right? Okay, I gave you lots of room here. Where's the resultant shape? From the tail of the first. This is going to be V ground. Where's theta going to go? Bottom left or top right? Color. Good, solve this. What will the radar see this plane traveling as? Mr. Duick, I noticed that I found theta using tangent here. Well, yeah. And I used tangent here. Well, yeah. And I use tangent here. Well, yeah. Will it always be tangent? No. Will it usually be tangent if I'm making up simple examples for you? Yeah. But don't take that as a rule. We're going to get tougher as we go. But it'll still usually be tangent. A much more interesting question. So before we had GPS, most jetliners actually had a navigator. There was a third person in the cockpit, or they were called the flight officer. And it was their job. Really, the airplane isn't as interested in this. They know what they want their ground speed. Here would be a better question. Suppose the wind is blowing east and the plane wants to go due north because that's where their destination is. How should they point the plane? In other words, they would want to calculate this if they knew that and that. How would you get this VE by itself? Yeah? How do you subtract vectors? Hold that thought, but that's something we'll have to think about. How do you add two vectors together? Easy. Tip to tail. How do you subtract vectors? Spencer also asked a great question earlier. He said, hey, Mr. Duick, how would you add three vectors? So here it is. I see directions and I've scrolled down, so I'm going to draw a compass rose. Three forces. The answer, the question you asked and the answer is more complicated than you realize. Look up. What's 3 plus 6 plus 7? How do you add three numbers? I don't know if you thought about it. There is no way to add three numbers at once. You add two of them, get an answer, and then add the third one. There's no algorithm that lets you add all three at once. However, sometimes the order that you choose to add them can make things easier. If you were clever, how would you add these together?
7 plus 3 is 6.
Okay? 7 plus 3 plus 6 is probably, okay. How am I going to add three vectors? I'm going to add two of them, get an answer, add the third one. However, sometimes the order that I choose to add them in can make my life easier. Kiana, what's the first vector, magnitude and direction? F1. 5.5.
5.5.
Yeah, by the way, can you see if you're in a rush? It would be very easy to read that as 5.1 north. Don't do that. I'm sorry, that's a silly mistake. Don't do that. So, sorry, what was it? 5.5 south? Okay, I'll dump. Plus, what's the next one?
8.6 west.
A little longer than 5.5. Plus, third one?
10.6 south.
I'm going to add these three together, but can you guess which two vectors would I be clever to add together first? Yeah. You could, by the way, add these two. You'd get a slanty answer and then add the slanty answer to this using the sine law or the cosine law, and you'd get the same answer, but you'd do about 5 extra lines of work. So what I would, or what if this was pointing, what if this one was pointing up? No problem. I would just go winner minus loser, but I would still add the north-south ones, and I would combine any east-west ones into one. Then I would do my vector math. Okay? So this is the same as 16.1 plus 8.6. 8.6, roughly half of 16.1, so I drew it about half as long. How many vectors do I have now, Spencer? How do I add two vectors together?
Pretty simple, tip to tail.
In other words, we turned 3 into something we already knew how to do. Look up. I started to draw the first vector, and then I went, oh, wait a minute. I'm going to run over my equal sign. I usually try and imagine what the vector drawing is going to look like, and I realized I'm going to need to move that 16.1 over a bit so I have enough room to draw the 8.6 and not run into my other drawings. There's the resultant, FR. Solve it. Oh, where's theta going to go? Bottom left or top right? Color, 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 color. Mr. Duick, yeah. How would you add vectors together in 3 dimensions? Tip to tail plus tip to tail, get a resultant tip to tail. And there is actually 3-dimensional trig. There's a whole branch of math doing that. By the way, can you see why if you're doing this on almost every question, I said yesterday, you're going to get really good at trig?
Yeah.
And if you can get good enough that you can do most of it just on your calculator in your homework, go ahead. On a test, on a quiz, show your work so you don't make a silly mistake. Is it right? 18.3 newtons, 28 degrees west of south? Or 62 degrees south of west? So on the next page, I asked, how would you subtract 2 vectors? We're going to talk about that tomorrow, Monday. One of my favorite comics is Foxtrot. The author, Bill Ammond, actually has his physics degree. And so it's about a family. The youngest boy, Jason, I identify with. He's the resident nerd. So he's wearing the football helmet, playing football with his older brother, Peter. And Peter says, Jason, what pattern did I tell you to run? Jason replies, you said go 10 yards out, then 10 yards to the right. And what pattern did you run? Well, I went 10 root 2 yards at a 45-degree angle. And are they the same thing? If you add the vectors, sure they are. This is football, not math class. Why do you think I rounded to 2 decimal places? Now they're playing football again, but this time Jason is the quarterback. Jason says, okay, here's the play. Go 40 yards downfield, then turn left and go 20 yards, then turn right and go 25 yards, then turn right again and go 30 yards, then turn right and go 30 yards, then turn right left and go 10 yards. Then turn left and go 15 yards, then turn left and go 20 yards, then turn left and go 50 yards and hit with the ball. Peter thinks for a while and he says, won't I be right back where I started? Jason says, I can't throw very far. I have taken my students out to the field. We have run this play, and you do end up back where you started from. It is a vector sum of 0. But we're not going to do that today, sorry. I know, Owen was like, can I run this? Can I? No, we're not going to run it today. What's your homework? You're going to get a quiz. Sort of. Home quiz. I've given you 4 generic vectors. Vector A, B, C, and D. You can assume A, B, and D are all the same length. All I want you to do is draw the pictures correctly. You're not going to do any trig, any Pythagoras. I'm going to assume you've mastered that. Step 1, I got to be able to get you to draw the diagrams correctly. So A plus B, how would I add those 2 vectors together? Draw them. So if you go like this, and if you go like this, and then you say, there, that's the answer, I will not mark that right. I will be fussy. You must put the arrow on the end of your resultant so that you've told me that you know which way it's pointing. So all of you will get question 1 right because we just did that one together. Then there's 2, 3, 4, 5. I haven't talked about 5. It's a bit weird. See if you can figure it out. Same with number 4. Here's a 3-vector question. See if you can figure it out. How do you multiply a vector by a constant? I haven't talked about that. See if you can think about what would make sense to you. We'll go over the answers next class. Also, if you haven't finished the math homework from last day, you can try that too. When does this class end at? 1:30. So you got 10 minutes. You can probably get her all done in class. Let me first of all pause the video.